The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Good afternoon, everyone. Welcome to the second part of the session, The Art of Designing Ductile Concrete in the Past 50 Years, the Impact of the PCA Book, and Professor Mete A. Sozen. Before we get started here, we have the learning objectives, which are also listed in the program, the convention program, and you can read them either here on the screen or in the program. Now, I will take some time to introduce our first speaker because it is the honoree of this session, Professor Mete A. Sozen. So we have not been introducing in detail the other speakers, but I think Professor Sozen does deserve to be introduced properly. So for me, it is a great honor and a pleasure to have participated in the organization of this session, especially because it celebrates the 50th anniversary of such a revolutionary book as the PCA book, but also the many contributions of Professor Sozen to the field of reinforced concrete and earthquake-resistant design. Now, Professor Sozen obtained his BS degree in Turkey from Robert College, and his master's and PhD degrees from the University of Illinois, and under the guidance of Professor Sis. He has taught for over 50 years, first at the University of Illinois from 1957 to 1994, and then, since then, at Purdue University. Now, while Professor Sozen was at Illinois, he continued the work of some of the greatest minds in the field of reinforced concrete and earthquake engineering. And just to name some of them, we have Professor Frank Richard, Hardy Cross, Harold Westergaard, Nathan Newmark, Chester Sis, and just again to name some of the most notable ones. And not only he continued with their work, in some cases actually he was a close collaborator, as was the case of Professor Sis and Professor Newmark. Now, Professor Sozen has been arguably, at least in my opinion, the most influential researcher in the field of earthquake-resistant design of reinforced concrete structures. And I'm going to name a few of his major contributions. Some of them have been already being discussed in the first session. But we have, first of all, the development of the most widely used hysteresis model for simulating the behavior of reinforced concrete structures on the earthquake, which is the Takeda model. The use of equivalent damping and the substitute structure method, which was the topic of the very first presentation in the first session, and its application or their application to displacement-based design and performance-based earthquake-resistant design for limiting damage during earthquakes. Understanding the mechanisms of shear strength degradation in reinforced concrete members with displacement cycles, and the development of methods for a rapid evaluation of vulnerability of structures during earthquakes. Further, Professor Sozen created the earthquake simulator at the University of Illinois, and that allowed him and many other researchers to study more in detail and conduct pioneering research on the behavior of structures under ground motions. Now, besides his many research contributions, he's also made outstanding contributions to the education of generations of civil engineers and particular structural engineers. Some of them have held leading roles in the profession, both in design practice as well as in academia. And I'm just going to take the risk of naming a few. I know most likely I will, well, definitely I will miss many of them. I hope I don't miss any of the ones that we have here. But just to start, we have Professor Peter Gergerly, Professor Jim Yirsa, Professor Neil Hawkins, Professor Otani, James White, Jack Maley, James McGregor, Sharon Wood, Polat Gulkan, Kathy French, Said Saidi, Michael Krieger, John Bonacci, Roberto Stark, Adolfo Matamoros, and Santiago Pujol. Did I miss anybody in the audience? And Joan Browning. I should have said Adolfo Matamoros and family. So anyway, for me, it is a great pleasure to introduce to you Professor Sozen, who is the first presenter of this session.
Thank you very much. You know, after this introduction, the best thing I can do is say thank you and sit down. I don't want to ruin your impression by speaking to you about it. But I don't intend to speak of myself. I'm indeed thankful for you to come here on a Sunday and tolerate our presentations, which so far have been excellent. But I don't promise that they're going to go on like that. And I would like to express my sincere appreciation to those three people who are not here, cannot be here. Dr. Blume, Dr. Newmark, and Mr. Leo Corning, for letting me work with them. And actually, for me, it was a re-education to have the privilege of doing some of the menial work as this book was being prepared. Let me give you an informal perspective of why the book happened. You see, I have been told from various sources that up to about, I would say, 40s, concrete was used where it should be used. It was used in driveways, and it was used for decoration in two-story homes, and there were a couple of buildings too here and there. But then came World War II, which, as you see from this photograph, done by our very strong public relations services, was a picnic. It was a ball. It was a delightful thing in which we went and saved nations and gave them freedom and democracy. But during that time, I'm told, steel became a very rare element, so that it was not sold anymore. It was rationed. It was given to people that the steel industry preferred. So they didn't feel there had to be competition. And then these tricky concrete guys started creeping in with buildings. It was true, there had been reinforced concrete buildings before, but suddenly the situation was open for them to build reinforced concrete bridges and moderate to even high-rise reinforced concrete buildings. I am not sure when the steel industry took notice of it, but suddenly there was a very strong trade war. They decided, I think it was in mid-50s, that they decided they had to take a position toward the concrete industry. And the first explosion, the first attack, if you wish, was in that document that I believe Terry quoted earlier in the game, although I thought it was put out in Los Angeles in the mid-50s, that buildings more than 160 feet in height shall have a complete moment resisting space frame. And of course, the frame had to be made from a ductile material. And the necessary ductility should be considered to be provided by a steel frame with moment-resisting connections. And that was that. Now, After all, Dr. Newmark had been talking about ductility for some time. You needed a ductile material, and it was quite clear that if you compared steel with concrete, concrete looked like a nonentity. It was a nothing. And there was no argument about how buildings should be built. And then a very prominent structural engineer in California repeated the same things, and it really exploded like a bomb, that a ductile frame was needed to back up a shear wall, and that steel is tougher than concrete. Well, you saw how much tougher it was, that there was no connection between them. And by the way, until then, everybody was talking about absorption of energy, which was really the wrong term for earthquake works. It was dissipation. But anyway, steel was so much the better. Now, by that time, the concrete industry thought they should do something about it. I'd like to take a few minutes to tell you my perspective of the people who took part in this trade war. First, there was Leo Corning, who was the chief structural engineer of the Portland Cement Association. And you know, at that time, Portland Cement Association did technical work to help the profession. I was depressed to hear yesterday that Portland Cement Association is dropping Chicago and going to Washington, D.C. in order to become a lobbyist agency and forget about all the technical work that they have done. And I hope I'm wrong. I hope what has been told me is wrong. But that's what they tell me. Anyway, Leo Corning took his advice, I believe, from Steve Barnes of Los Angeles about what should be done. And I was told that Steve Barnes said John Blume, a very colorful and delightful structural engineer, should be involved in it. And John Blume suggested that Nate, Dr. Newmark, should be involved. Dr. Newmark, I know, wanted very badly to have George Hausner in the book. And George Hausner did consider it for a little while, but then said, I is not going to get involved in commercial enterprises, and quit. It was out. John Blume, insofar as I can remember, had a supporting team made up of Sig Freeman, Joe Nicoletti, whom I always admired. His father was a winemaker, and I always wish he had stayed in that game. And Roland Sharp. Nate started working with Art Feldman and Chet Cease. And Leo had as his technical team Al Parham and John Sparunis, who I think made some very important contributions. Now, in terms of the intellectual environment, I would say that it came from Lydic Jacobson of Stanford, going down to Blume and going into the book. Hardicross, Westergaard, and Frank Richard, who essentially trained Nate Newmark. And Bio, Martel, Hausner, and Hudson were always in the game because they were, after all, the inspirers of the scientific environment. And I think Terry was talking about the Los Angeles formula, the one that varied with the height of the building, which came from the first statement of the response spectrum by Bio at one time or the other. But they were always in the background. And Dr. Minami, who provided the connection between Japan and the United States. And would you believe it? I always thought Dr. Minami was Japanese. I had listened to him several times. I had been in meetings with him. But it turns out that he's a Californian, that he was born in California, went to school in California, and his first name was John. I didn't know it. And he went to Japan later on. And then there was Dr. Siohira, who came here in the 20s of the century, really to give lectures about earthquake engineering, primarily in Western universities. And behind that, there was Mikishi Abe, who worked at Illinois, again in the 1910s. and did provide a bridge between, an intellectual bridge between Japan and the United States. Now, I'm sure I'm missing somebody, but this was, if you wish, the original team that led to the book intellectually. Now, the real attack by the steel industry, other than working through the codes, was when the Agadir 1960 earthquake was in view. It was a very small earthquake, magnitude 5.7. It's lasted 12 seconds insofar as I remember, but it devastated the city of Agadir, which was almost all reinforced concrete. And the steel industry was so much interested in science that they rushed out with a team out there to take pictures of buildings like that. And the steel team included some elegant people like Dr. Clough, who went out there to study steel, but there was no steel construction. And this was repeated later on, and as I think Jim or Mike mentioned, but this was the attack. Now, finally, in 1961, the book came out, and I would like to shorten my statements about the book because much of it was already said. But I would like to mention Dr. Newmark's spectrum, the tripartite spectrum, which is really very simple, but very difficult to interpret from that figure. Nate did everything in very simple terms, but somehow when he spoke about them, made them complicated. I don't know why. Maybe that's what works. It's possible. And I would like to say this, that I've heard, and I'm sure you're all familiar with it, I've heard many criticisms of this thing, of saying it doesn't fit this, it doesn't fit that. But people who criticize it don't realize that this is a design spectrum, not a scientific spectrum. And as a design spectrum, it is still damn good. And shouldn't be criticized, but it was a brilliant move. Let me tell you something personally. I think that the week he had discovered this, I was working with him on another problem. And he was so excited that he started explaining it to me. I didn't understand what he was telling me. I swear to you, I had no idea. But of course, he was the boss. And I sort of nodded my head, and it took me a month or more later on to understand what he was talking about. And let me tell you this, even now I'm not so sure I understand it fully, but it works. As a design spectrum, it is elegant. And his concept of the response of steel or concrete or anything was elastic plastic. And in my small size, I used to try to tell him and say, this is not true. And he would say, don't waste my time with those things. And so help me God, he was right. And I think back now, he was correct. And of course, he talked about ductility. And the mantra was 4, although you seldom see it written any place, because it's a very vague mantra. It flips back and forth, depending on the application. But look, I'll take credit for these tests. I designed those tests that several of you talked about. I was wrong. These were irrelevant to the earthquake case. However, they did provide some information. They did provide that our simple Newmark type approach didn't fit reinforced concrete. And first, of course, that you couldn't relate the ductility of concrete to the stress-strain curve in compression. There is no correlation between them. But still, when you see the theory of the time versus the actual behavior, you say there's something wrong. And this was one of the questions that came out of this book, but there wasn't time before the publication of the book to go further into it, so that blue line was left like it was the theory itself. Then there arose some questions, very simply put. Newmark and Blume didn't say, give us collapse consistent protocols of virtual hybrid experimentation, they simply had questions like this. They said, are we really correct in assuming that the strain distribution over the section is linear? Is unit curvature a measure of ductility by itself, which was being used at the time the book was published? That was used as it was. Does reinforced concrete really respond elastoplastically? This was before the tests were being done. Simple questions. Is rotation ductility the critical issue in determining a design? It is, I'm talking about, was the structure that should talk about the limits of the design, or the non-structural elements? And other issues like that, I'll talk to you about them again. And is concrete compressive strain limited to 0.04 or even less? Didn't know the answer. Is strength and shear under load reversals to be treated as monotonically increasing shear? This is what Jim and others talked about earlier. In comes Dr. White. He's not here. Well, good. I can talk about him viciously. He's in a very negative mood. He designs a test specimen that, by the way, looks right with respect to the earthquake system, because now the loads are reversed on both sides. He comes up with hysteresis plots, as you see in here. And there is no resemblance to what Dr. Newmark has been talking about in getting all these very strong conclusions about the test. That's, if you want to idealize reinforced concrete under cyclic loading, that's what you should do. And by the way, I take this up to Dr. Newmark, and he says, don't you have anything else to do with your time? He actually said that. I will not talk about the shear problem. I think you've heard it enough, although this one is being used as the capacity design spectrum invented by the New Zealanders all over the world, but it came out in that book. But look at Jim's answers to all these things. A linear strain distribution, he says, niet. Is unit curvature a measure of ductility? He says, no, there are lots of other things that determine how you should design, rather than just the ductility of the structure, which blows the steel industry out of the water, in a way. Does reinforced concrete respond elastoplastically? Well, you know the answer to that. Is rotation ductility the limiting factor? Hell no, he says. Is concrete compressive strain limited to 0.04? No, he's talking about 1% that he has measured. And shear, again, no. But look, in one case, he actually responded positively. And I regret very much that this hasn't been recognized by the profession. He plotted the tensile reinforcement strain versus deflection. The strain plotted as a function of the yield strain in the vertical axis, and deflection plotted as a ratio of the yield deflection in the horizontal action. And you see there is a jump at the yield point. And he measured this, and he explained it in terms of plane geometry to show that that is why it wasn't elastoplastic. That is why the flat top part of the stress-strain curve was being essentially wasted in air. And I still think that for that observation, if he had been a physicist, he would have gotten a Nobel Prize. But unfortunately, we don't even recognize it today. But that was positive. Then there were tests by Professor Ockelston of Johannesburg in 1956, when he tested reinforced concrete frames with and without filler walls. And he found out that with filler walls, a reinforced concrete frame had to be detailed properly, because he had rather negative results from his tests. Well, in comes Dr. Fiorato and essentially repeats the same tests in scale, and finds that indeed if you detail them properly, you can get as much as 2 or even 4% drift from such systems and get a lot more strength if you're interested in strength, although that is not the essential issue. And what's more, he provides really a brilliant definition of determining the strength of a reinforced concrete frame with a masonry wall in it. But the minute he finishes this work, he turns his back on it and never looks at it again. But fortunately, the work was continued at other places, and they did something out of it. Now, to me, although Terry, I think, gave you a very good explanation of it, the interesting part was the question about drift. And if you look at this book today, and it's still worth looking at, you find that there is a tremendous controversy going on in the pages of the book about drift. Because on one side, Nate Newmark starts by saying, I need a ductility of 4. And that means you need a deflection of 4 times the yield deflection at least, if not more. And yet, in other parts, there is no sound. There is a wonderful discussion in 1959, a report of the Southern California Structural Engineers Association, in which they ask, what is good engineering practice related to drift? Now, this is in 1959. And they say, well, if you're talking about broken glass or wall pieces falling, that's within engineering concern. But if you're talking about protection of non-structural elements and motion sickness of the people in the building, that's paternalism. And you know, that was the attitude toward drift at that time, because it was considered to be very small because it was calculated for equivalent lateral loads that were no more than 7 or 9% of the weight of the building. So drift was not a problem. And yet drift was a problem because Nate was talking about 4 times the yield displacement. Now, in the book itself, and I quote directly from it, they say, even though drift is seldom critical in a multi-story reinforced concrete building, you can ignore it. But then there is a less rigorous, as if the other one is rigorful, but anyway, a less rigorous rule that may be more accurate. The word accurate should never be used in our profession, but there it is, more accurate, is to sum story drifts corresponding to yield deflection and amplifying the yield deflections of the first 2 stories by 2. So wait a minute, huh? Why can you say on one part it's negligible and then you take the yield deflection and amplify it by 2? So there was a strong question going on that went on. And then John Blume comes in with his reserve energy technique, which really was elegant for the time. He says current design methods fall short of estimating drift, which is negligible. So what? Huh? Are not sensitive to damage caused by drift, ignore changes in natural period, do not recognize the effect of repeated loading, all about drift, insensitive to non-structural elements, and do not consider energy, maximum drift, and permanent set and damage. He said, we are blind to the eyes of arrows. But at the same time, they say, it's small, and for multi-story buildings, you don't have to worry about it. And this really set up the question about drift. This picture that Terry showed you, I don't have to get into the detail. Then there were many years of research. And again, I'm sure I'm forgetting the names of some of the people involved, which did a lot of work on dynamic testing of reinforced concrete frames to develop an impressive database about the relationship between ground motion and drift, because that's something that you could do in small scale. Now, as a result of this, Dr. Algan essentially did the first work saying design should be based on drift in around 1980. By the way, two irrelevant things. Dr. Algan now is one of the outstanding yoga teachers in the United States. But he is a very creative guy. He goes in every direction. And I should also tell you that getting ready for a lecture about Emilio Rosenbluth last year, I discovered that both Emilio and Nate talked about drift being the important thing in design in the 60s. But they never wrote it down anywhere else. I found this in their private papers. But anyway, the first, I think, shot that I heard was from Dr. Algan. And then Dr. Eberhard talked about behavior-based design of reinforced concrete columns, which, as Terry was saying, is essentially performance-based design later on. And let me finish with an interesting setup. Dr. Shimazaki, looking for a very sophisticated way to calculate drift by using the Takeda hysteresis, discovered that he could calculate the nonlinear drift by using a linear model based on 2% damping. It was that simple. The only thing he had a problem with was in the lower period range, in the nearly constant acceleration range, which he couldn't straighten out. And then in comes Dr. I never know how to pronounce his name because he keeps changing it. It's either Lepage, Lepahe, or Lepache, whatever his name is, comes in, and it's very much like the Christopher Columbus's egg story, you know, where he drops the egg on the table. He says, no, you can do the whole thing with a single straight line. Use a linear model, which was elegant, and I still believe in it. But then after the 1999 earthquakes, we go back to what was done in that we have, by Osterk, we have a change point depending on the peak velocity and base shear strength, but still, you can still, quote, predict, if you know what the earthquake motion is, the drift of a building with a linear model. And I think that really closed the answer, essentially provided the answer to what Newmark and Blume had been asking about. And I think it turned out to be one of the useful results of this thing. Now, I would like to remind you once again that it was because these guys asked very simple questions that we were able to get the answers, not sophisticated ones. And William Stafford, a poet in Kansas, has said that every war has two losers, if only two people are involved. I think a trade war has many winners. And in this case, the concrete industry won as much as did the steel industry. Thank you very much. That's all I want to say. And a trade war is the only kind of war I like.